Hi everyone. My name is Zhaocheng, a DPhil student at the University of Oxford. Today I will talk about our project, LeoNet, a binary pulsar detection network. And binary pulsars are extremely valuable in astrophysics, especially for testing general relativity. However, they are also very difficult to detect because in a binary system, the pulsar's orbital motions causes Doppler shift, which spreads the signal's power across multiple Fourier bins in the frequency domain. And this smearing effect makes the traditional detection methods much less effective. And one common approach for binary pulsar detection is FDAS, which is Fourier domain acceleration search. And FDAS uses method filtering with hundreds of trace filters to correct for the Doppler shift, assuming the constant acceleration. And this assumption is valid only when the observation time is shorter than about 1/10 of the orbital period. And FDAS can produce an F dot plan to locate the possible pulsars. And on the right, we can see an example of a simulated F dot plan. The bright point in the middle indicates a binary pulsar with an acceleration of 100 and an initial frequency of 500 Hz. So FDAS is accurate, but a little computationally expensive, which limits its use for the real-time detection. And this slide shows the full processing pipeline of the LeoNet. We start from the dispersed time series data. And if the observation time is shorter than 500 seconds, we need to zero patch it to make all samples constant. We picked 500 seconds because it gives a clean Fourier bin size of exactly 0.02 Hz. So it's a fine value, which make it much easier and more precise to locate where the pulsar signal lies in the frequency domain. Unlike, for example, 600 seconds, which would give a repeating decimal bin size. And yeah, if the observation time changes, the Fourier domain size, Fourier bin size will also change. So we would have to adjust the template resolutions for each time. And padding all data to 500 seconds keeps the frequency resolution fixed and allow a single set of templates for all data with a different observation time. And then we perform the Fourier transform and split the spectrum into blocks of 4,000 points, and each covering about 8 Hz. And the reason is that the full spectrum is huge. Splitting it reduces the input size and the model complexity, and making training more efficient. To avoid losing a feature near the edges, we add some overlap between blocks. Specifically, we add 100 points on both sides of each block using the neighboring values. So signals close to the boundary are not cut off. Um, and during training, since we know the pulsar spin frequency, we select the block containing that frequency as a positive sample and random noise blocks as negative. During inference, since we do not know the pulsar's frequency, so we have to check all the blocks to make sure no signals is missed. And the key part is the template layer convolution. And each template has 201 points, and which corresponds to the setting of Z max value equal to 200 in FDAS. And Z max represents the maximum frequency drift caused by the Doppler shift of the binary pulsar during the observation. So by using these points, we ensure that the LeoNet template covers the same frequency drift range as FDAS, allowing fair comparisons while keeping the design consistent. And all templates are learnable, so the network can automatically optimize them for method filtering. Finally, the model outputs the spin frequency range of the detected binary pulsar candidate. Yeah, and this is a training data construction. Currently, only a small number of binary pulsars have been detected. So real data alone are not enough to train a deep neural network effectively. So we use SIGPROC to generate synthetic data and build a balanced dataset. And the table on the right shows example parameter settings. And this ranges based on the value reported in the Pulsar catalogs, but we slightly broaden them so the model can also learn from more extreme conditions. And to make the network adaptable to various observation setups, we generate data with observation times from 100 to 500 seconds and sampling time from like 128 microsecond to 1.31 millisecond. And this diversity improves the network robustness and generalizations to the real telescope data. Um, and here is the architecture of the neural network. And it has two main parts, the Doppler shift elimination part and the classification module. So on the left, the real and imaginary parts of the Fourier spectrum are processed by the template layer with 10 learnable templates, and each corresponding to an acceleration up to the max value equal to 200. And after convolution, we take the absolute value to form the FF dot plan. The field modulation block then takes the observation parameters as input and outputs two factors like beta and gamma to scale and shift the features map, allowing the model to adapt dynamically to different observing configurations. And finally, the classification module extracts the features through convolutional layers and outputs the predicted spin frequency range of the pulsar. And And here's our training strategy. So during the training, we reduce the weight of samples with very short observation times and large sampling times. Since their signals are usually too weak and may distract the neural network from learning meaningful features. We also use the neural architecture search to automatically determine the optimal number of the templates in the template layers, which is 10, and balancing the performance and the computational efficiency. Because if we have more templates in the template layers, the inference speed will be decreased. So for the inference, we only process data with observation times longer than 200 seconds because short observations rarely contain enough information to recover the binary pulsar features. We also skip the frequency below 100 Hz since our goal is to detect the millisecond pulsars, which lie in the high frequency band. These restrictions reduce the false positive rate and also improve the efficiency. Finally, by combining results from all blocks, the neural network determines the frequency range where the binary pulsar signals is located. And here's some results. So in most observing conditions, the neural network achieves a lower false negative rate than F does. When the observation time is short for like 200 seconds, F does perform slightly better in some cases. Like when the sampling time equal to 256 microseconds. However, as the observation time increases, the performance of the neural net improves significantly and quickly surpass F does, showing a strong ability to recover binary pulsar signals when longer observation time are available. And the false positive rate of the neural network is fixed to zero through the threshold calibration. So these comparisons purely reflect the detection performance. And his speed. So for FDOS with the sampling time like 128 microseconds and the observation time of 500 seconds, one observation takes like about 18.3 seconds per observation. And in contrast, the LeoNet takes only about 3.9 milliseconds per observation on an NVIDIA A100 GPU using TensorRT. That's more than 4,600 times faster, making the neural network ideal for the real-time and large-scale Pulsar servers. But the neural network still has some limitations. Because our neural network mainly focuses on detecting individual harmonics below 1,000 Hz or below the Nyquist frequency. So in most cases, pulsar energy is concentrated in the fundamental frequency. So this design works very well, and that's why we describe the neural network as designed for the fundamental frequency detection. It can also detect a strong second or third harmonic if it falls within 1,000 Hz. However, if the signal energy is distributed among many weak harmonics, the sensitivity becomes lower. And in the future, we plan to incorporate the harmonic summing mechanism using the recurrent neural network or transformers to model the relationship between the fundamental or harmonic or higher harmonic frequencies, improving the sensitivities to the short duty cycle signals while maintaining the LeoNet's faster inference. And to conclude, the neural network provides a faster and effective alternative to the traditional methods like FDAS for the binary pulsar detection. It works reliably across different observation setups and process data thousands of times faster and make it suitable for the real-time servers. The main limitation is the absence of the harmonic summing, which we plan to address in the future to improve the detection of more complex pulsar signals. And thank you for listening. And yeah, I'm very happy to take any questions.
Thank you very much. Questions for the speaker? Maybe I can ask the first question. So can you please comment more on the specific templates that you're using for searching? So you mentioned that for match filtering, there are certain templates, right? And probably you're injecting in signals into your synthetic data using certain templates. So can you comment on whether they are like some numerical relativity surrogate models or what are they exactly?
So for the synthetic generation, so we like we use the SIGPROC to generate the pure noise data as our negative samples, and also we use the SIGPROC the fake command to generate like the binary pulsar signals, and we have a we know the frequency of the spin frequency of the binary pulsars previously, so we just locate the position of the spin frequency in the spectrum. So we pick this as our positive samples, and to build a balanced data set like 10,000 positive and 10,000 negative, and we can say the and for the conditions here, we using one hot to represent the sampling time, like 100 represents the 128 microsecond, and 0100 like something like this to represent the 256 microsecond. And if you want to use the sampling time like 150 microseconds to do the inference. We in principle we use the higher level of sampling time to do the inference. Like if you want to use 150 microsecond to do the inference, you need to set the conditions, the metrics like to 256 microseconds. And one more thing I want to talk about is we use 100 seconds data to do the training, but we do not inference or evaluate any data with the observation equal to 100 seconds because we add this low, very faint signal, very weak signal into the neural network because we want the neural network to have a more robustness when it facing the low signal to noise ratio data. Yeah.
All right. Thank you. I see there's a question online. Ramesh, can you please unmute yourself and ask the question?
Hi, Zhaocheng. I hope you can hear me.
Yeah, I can hear you.
Yeah, so yeah, it's a very interesting approach, and I think similar sort of, I think maybe similar sort of thing also mentioned probably early on. So you mentioned that one of the shortcomings is mainly it's not sensitive to harmonics, and so my question was, have you been able to test it on some real data yet, or is it like too premature?
Yeah, we do test some real data, and we only tested like only one real data. But I think in the future we need to test more real data in the future. And if we got the real data, and we can just easily put it in our pipeline to do the test.
Yeah. Okay. Right. No, I mean, I was just curious that even you mentioned that, that reason why you need injection, because there are not too many sources, but even in the available sample of binary pulsars, there is a pretty good range in terms of their signal strengths and acceleration and pulse shapes. So that's still like quite a good sample to stress test the approach. That's my feeling, but maybe like you will have some more sensible thoughts. Yes.
Yeah.
Thanks.
Thank you.
Are there any more questions?
Yeah, maybe Zhaocheng, just one thing I have, like you say your template is like 200 points long, and you have 10 learnable templates, correct? So, so I'm just curious to understand that trade-off between them. If you increase your acceleration range, like right now you are going for a 200 wins acceleration correction, correct? If you increase the range, or if you introduce a one more dimension, how you actually going to play with these templates? Are you going to increase the template length, or are you going to increase the learning number of templates? Any kind of thought on this?
I think for the neural network, I think it's do not need to change the length. But if you want to change the frequency drift value to very high, like 800 or something like this, I think it might be you think about to increase the template, the length of the template. But the reason I chose 200 is basically it's kind of trade-off of the overfitting problems and the performance. So for at now we set the target drift value is 200, but the neural network can detect more, like if the data even if the data has a more frequency drift, like and when I also do some tests for the by using FDOS, like to set the Zmax value equal to 500 and do some tests, and some data can be founded by FDOS and also be founded by the neural network. So the neural network has a very nice generalizations for the binary pulsars, even if they have a very high Zmax Z values.
Understand that learnable template is kind of fixed. You are going to change the length of the template.
Yeah, the template can learn it by itself to optimize the parameters and to let the template fit suitable for very high Z values.
Okay. Are there any other questions? I guess since we have time, I'll ask another question. We know that match filtering should give you the optimal performance regardless of SNR of your injection, at least in the scenario of just white noise. So have you tried to benchmark the performance of LeoNet pipeline against the performance of, let's say, match filtering and test whether or not it's SNR dependent? I would assume it is, but I would like to understand what SNRs it would start degrading in terms of its performance.
You mean to do some tests on different signal to noise ratio?
Yeah.
Yeah, we do the test, and even in the low signal to noise ratio part, the performance of both methods like LeoNet and the FDAS are decreased, but the performance of LeoNet is still higher than the FDAS. So, and even though there are several we can see there are still several signals can only be detected by the FDAS. I think it is basically because the harmonic summing mechanism. So for in the lower, low signal to noise ratio signal, the fundamental or the higher harmonics frequencies, the power is very low. So for the single harmonics is quite low for the LeoNet to classify it as a positive. So I think this is another this decrease of the performance is basically due to the absence of the harmonic summing mechanism, but the total performance of the LeoNet is still higher than the FDAS.
Oh, gotcha. Thank you so much. I guess we are doing great on time. Let's thank our speaker again.